Welcome, class. I thought I'd try to make some more videos for you guys, hopefully to make things easier. These will be smaller chunks, and you can put them on as you need them, partially because this is a hybrid class, so there is that aspect outside of the classroom that you have to take care of. So let's kind of get started. We're on chapter 4 or 5 for this. Nope, it still shows me in that. Let's do that. And it should. There we go. Why did I divide sine by tan? Just cause. Okay, so this week you have the Alex test prep for homework that's due. Check the announcements with the proctor's schedule so you guys can get in there and make sure you get that done. Homework 4 is due next week in my office. This is going to talk about homework 4 and by Friday. Uh, and then also this week you have a secondary mathematics and incorporating faith in work essay due this week. We'll talk about that in class also. And then we have the NES test prep reflection. This is the one where you reflect upon how much time you've been giving to it, how successful you were on this test prep versus the last ones, those sort of things, what you know you still need to study for. And that's due by next Wednesday. Student work presentations will be in class. We'll be doing them about every other week. So make sure you know where you are on the schedule. And there's the schedule. You guys can look back at it. This week we have Brooks and Faith. And then in 2 weeks we have 3 people. We have Layla, Hannah, and Ashley. And then we have 4 people. And then we only have 1. So, nope, gonna skip that. We'll talk about that in class. You can look back over it. You can pause it, all that stuff if you want to. It's basically just pulled from the Halo. Triangles, circles, and trigonometric functions. So trigonometric functions, my hope is you guys are familiar with these. At some point, you have seen these. These are not new. And they all come from this idea of a triangle, specifically a right triangle, but these properties apply to all triangles. Sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. I always think of sine as oppositeness and cosine as adjacentness. Is that really what they mean? No. We'll get into that a little bit. Tangent is opposite over adjacent. This is how most of you probably memorize some idea of this. SOHCA, TOA. Sine is opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over hypotenuse. If you think of sine as oppositeness and cosine as adjacentness, you don't even have to think about that. But that is a nice way to do it. And you'll notice in a unit circle, your r is always 1. That is the radius of your circle. That's actually why we use r, if you didn't know. Tangent is sine over cosine. So a sine gerene over a cosine gerene is equal to a tangerine. I'm punny. Also, tan of theta is the slope of the terminal side of theta, or the slope of the hypotenuse of a triangle, of the triangle. And hypotenuse is specifically only on right triangles. So if you say you're looking for the longest side, that's fine. It could be any triangle. If you say you're looking for the hypotenuse, you are already telling us that is a right triangle. So it better be a right triangle. Representations of angles. So some textbooks teach triangles first. In fact, I would argue that most textbooks do this nowadays. They teach right triangles first. And then some textbooks do teach circles first. Seen that. I don't think there's anything wrong with it. In fact, I think it works just fine. But that isn't how I feel like most of them do triangles and then right triangles. So you can now talk about circles. So you can now talk about waves. But I haven't seen a book that teaches waves first. I'm not saying there isn't one. I've just never seen one. I have looked. So, as with everything, some people connect with one representation more than others. You're going to be teachers. You need to know that. So, reciprocal trigonometric functions, what are they? Well, you'll see that the naming thing, cow, doesn't roll off the tongue as easily. Cosecant is 1 over sine or hypotenuse over opposite. Secant is 1 over cosine. Hypotenuse over adjacent. And cotangent is 1 over tangent or adjacent over hypotenuse. These are the complementary of the angle, the complement of the angle. That's where you get the cosecant. Cotangent is the complement tangent of the tangent. Fun footnote in the book. Ancient Hindus were the first to consider sine as a ratio of side lengths, which they called jiva, a shortened version of chord half, which makes sense. They considered them as a ratio of the side lengths. Arabs then translated this phonetically to jaib, which means curve or fold, which then years later would get translated into Europeans after the Middle Ages, or in the Middle Ages, when they started to actually look at the Arab mathematics and the Arab scholarship, and they translated jibe as sinus, the Latin word for curve. So does the word sine mean something? Kind of. I think of it, like I said, I think of it as oppositeness. I think of cosine as adjacentness. So cosine, cosecant, cotangent. These ones have more direct meanings. Cosine of an angle is the sine of the complementary angle. That really is it. Cosine is the sine of the complementary angle. Of an angle is the secant of the complementary angle. And cotangent of an angle is the tangent of the complementary angle. So they do relate more directly. What's tangent? Tangent tells you a couple of things. One, tangent tells you that if you're tangent to a circle or tangent to a curve, you are perpendicular at that particular point. So that can tell you some stuff. And this is the kind of the idea. It's related to a tangent line. It is. And if you look at the little circle here, you take a line tangent to the unit circle and calculate the distance along that line from the point of tangency to the point intersecting with the x-axis. So that's the idea. Secant is from the Latin word secare, meaning to cut. A secant line on a circle is any line that intersects it in two places. So same thing with the secant of a curve, though we usually would just consider that a chord. The secant function is the distance from the origin to the point where the tangent line intercepts the x-axis. If this line is extended, it cuts the unit circle in half. Okay. Periodic, repeating pattern, repeats exactly the same shape, exactly the same size, horizontally and vertically. I want to be clear on this because some things we think are periodic are not. For p greater than 0 is the length of one complete cycle. This is periodic. A function is periodic if for every x plus p, whatever that p is, that length of one complete cycle, it is the same as f of x for all x in the domain. So this means if I went forward, if I went plus by this p, dang it, come on, let me write. No, that's not what I wanted. Okay, go back. There we go. I don't know why that wasn't coming up. So if I go forward by this, now there it is, that p, whatever that is, 5, 6 something. If I add that, if p of e is equal to 6 something, then every time I have x plus p, it's the same as having f of x. It will follow the exact same pattern. This pattern from here back to here is exactly the same as this pattern from here to there. And it will continue. This one's not periodic. Like it bunches really tight up here and then slows down as we move across. So not periodic. To define the trigonometric function, one starts with an angle of theta and finishes with some sort of information about the corresponding point on the unit circle. So we are given the angle and then we say something about the point on the unit circle. To obtain the inverse trig functions, we reverse this procedure. We start with some information about a point on a unit circle, and we finish with an angle that corresponds to the point P. Example, if we're given that cosine of theta is equal to 1/2, we were asked to find theta. Well, there I have the cosine function, and we would be looking at where is it 1/2. And we can see that that happens in a few locations, right? It happens here, 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 here. So all of those are answers for theta. Now, I listed them as radians, but same general idea. This would be like, let's see how many I know. This is in radians, so this would be 30 degrees or pi 6. No, no, it would be 60 degrees. Pi fourth is 45. Nope, I was right. But we can see them there. Only one-to-one functions have inverse functions. We cheated with x squared and square root of x in the last homework. We'll cheat again. How do we cheat? Well, we looked at only certain intervals. So kind of the same idea. If we look at cosine, which is a wave, then secant we'll only look at under certain intervals. Basically, we can't look where our wave has roots or where it hits the x-intercept because that would be 0. And we have to be careful of that because secant is 1 over cosine. So anything that would make secant 0 can't be in, what would make cosine 0 can't be in secant. Same is true for cosecant, except for it's using the sine function. Tangent works a little different. Tangent already has restrictions on it. Tangent would be 0 or would be undefined at pi halves and every multiple of pi halves. So we have to be careful when we do cotangent, it actually shifts and our asymptotes would be pi and any multiple of pi. So we have to be careful there also. They also can look kind of different when we talk about inverses. These are not necessarily inverses of each other. These are just relational, reciprocal identities. When we go to really inverting a sine function, um, we have to restrict the domain. And so when we actually do the inverse sine function, here we have the regular sine function right here. And we have these values that we have to watch for because those create this over here, which is the inverse sine function. So sine inverse or arc sine or sine with the -1 up top is the angle whose sine is x. Same thing for arc sine. They're just different ways to note them, and we still use multiple notations for these things. So do be careful. Same with inverse cosine. You'll see the pattern and how it basically turns so they look more like a tangent function. Tangent, on the other hand, looks more like a cube root function. So there's a summary of them. You can look over them. If x is positive, the angle is in quadrant 1. If x is negative, the quadrant depends on which inverse trig function we are using. So keep that in mind. These are the inverse functions. Most people don't know these. I don't know that you necessarily have to know these, but you kind of have to know how to do them in case you need to. Here's some homework. As always, we're going to try to discuss some of these. Consider Sarah thinks that tangent of 2 theta is equal to 2 tangent of theta for all values of theta. Well, that's not necessarily right. So let's discuss possible sources for Sarah's misconception. It would be important to know uh, how that looks, maybe why this came about. And I would probably gather that this comes from the idea that tangent of 2 theta is equal to 2 tangent of theta over 1 minus the tangent squared of theta. So that's my guess, is that's why the misconception happened. It's important to know why it happens, but how do we show her then? How do you prove to her that that's the case? Well, so this is probably one of the sources. This is something I would discuss. But another thing might be to go through the calculations. Like, why not go through this? These two are equal to each other, then no matter what I do, they should stay equal to each other. Is that a fair statement? So maybe we should do some manipulations. I think I did that on the slide, so let me see. Okay, there we go. So we have 2 theta. We set it equal to 2 tangent of theta. This is her misconception. This is me taking this piece and this piece, and then replacing this piece with what I know it equals right here. So I replace that, and then I start manipulating. They should equal the same thing, so let's see what happens. If I multiply by 1 over 2 tangent of theta, then here, So I multiply by this on both sides. That's going to get rid of it. So that part's gone. And I'm left with 1 is equal to 1 over 1 minus tan 2 theta. So, okay, multiply both sides by 1 minus tangent squared of theta. So I get 1 is equal to 1 minus tangent squared of theta. So minus 1 to both sides, right? That's all I'm doing here is minusing 1, minus 1 to get my 0. 0 is equal to negative tangent squared of theta. So then where is tangent squared of theta? Well, that happens when theta is equal to 0, pi, 2 pi, any multiple. And then, so I basically, therefore, theta, when it is pi or n pi, where n is an integer, this would be true. And then what's part B? Help Sarah see that it's not in two ways. So we made the calculation. This really shows that. We discussed the source, right? One source. And here's actually two sources. One source is the similarity in this triangle, in this formula. That's one source. Another source is that it actually is true when theta equals n pi, uh, where n is an integer, right? So then it's true here and it's true here. So it's true in two different places. And then it says help her see two ways. So one, we have it in calculation here. If you had to draw this as a picture, I would honestly use Desmos, right? Desmos. Because you can put all that in there. You can put both of these two in there, 1 and 2. And a lot of people, right? Pictures. Pictures are not proofs. They don't show anything. The calculation is more of a proof for that, though I still wouldn't call it a proof, but it more justifies it. But a lot of people, like you can justify stuff with numbers and they don't necessarily believe they're true, which is sad in a lot of ways, but it happens. So I would genuinely just use Desmos. You're going to see that tangent of 2 theta, right? Tangent of 2 theta has a period of pi halves, right? So that has a period of pi halves. Uh, whereas the other one, what is it? 2. Well, actually, it doesn't really matter. It could be any multiple, but theta has a period of pi. So it won't quite work. What was the other question? Let's go back. What was the other question? Is it true that arctan is equal to arcsine over cosine, arc cosine? So the great part about this is asking, is it true? So to disprove, we only need one counterexample, right? All you got to do is, or you could try to prove it. So it's asking, is it true? So you either prove it or you prove why it's not. I would genuinely keep this very simple. And I would say, well, let's check x equals 1. Nice, easy number. We can do most of this. So this becomes tangent inverse of 1 equal to sine inverse of 1 over cosine inverse of 1. And you may ask why I chose 1. Well, I chose 1 because those are things I know, and I can do this. So that's the biggest reason. I know my unit circle. You guys should. This is equal to pi. Come on. pi fourths, which is equal to, well, sine is pi halves over 0. Uh-oh, I can't divide by 0, so this is undefined. The right side, this side, right, is what I'm talking about, is undefined. At x equals 1, whereas this at the same value is pi fourths. So no, they are not the same. And why? Because just like if you think about it, like tangent is uh, opposite over adjacent, right? And so that can be manipulated, but we have places where tangent doesn't exist, right? There's those holes, which is why it's periodic. That's why it's got asymptotes. That's why it kind of looks like that, right? That's a regular tan function with these asymptotes. So anywhere that would give us one of these asymptotes will break. So that gives us a good explanation. Covered that. Okay. And then again, here's the assignments. All right. We'll end here. I'll make another one or a few, and we'll kind of go from there. So pause, stop recording.